Welcome back. In this lecture, we are going to give you an introduction to informed search. Techniques such as breadth-first search and depth-first search give you the ability to solve the search problem to a certain extent. However, they are not informed by domain-specific knowledge. The idea with informed search is now you can start using information specific to a problem to get better results. So in this lecture, we are going to focus on the heuristic function, which is kind of the key idea that we use to get better search results. And we will discuss best first search in this particular lesson. And then a little bit later, we'll go over things like A star. So the key idea with using a heuristic function is you keep the goal in mind when selecting a path. If you remember techniques like breadth-first search and depth-first search, they are just expanding nodes based on either a first-in, first-out or a last-in, first-out paradigm. Here, we're going to start making that selection based on some information of how those nodes potentially relate to the ultimate goal of where we're trying to reach. And so the way we do this is we're going to use a little bit of extra knowledge that might help us pick the right path. And this is what's called a heuristic in this case. So the heuristic function is a non-negative estimate of the cost from of the least cost path from a given node to the goal. And we'll make this a little concrete in a moment, but basically it's an underestimate is the key thing. Of course, we want to make this efficient to compute. You could have a heuristic function that gives you the exact cost of a node to a goal. However, that would be the same as just doing something like breadth-first search. HN needs to be efficient to compute. So we're sacrificing having an exact value of that cost for computational efficiency. And of course, you can extend this to entire paths. And as I said, it is an underestimate. So that means that there is no path from that node to the goal that costs less than H of n. And then we will also discuss this idea of an admissible heuristic. And this in here, we can actually prove that the heuristic function is an underestimate of the actual path. If we can prove this, then we get some nice results about the optimality of the outcome of the search algorithm. Okay, well, let's start with an easy example to warm up. So let's say the nodes are points in the Euclidean plane, i.e. a map. And if you have a map and you have roads, the distance between 2 points is going to be based on the shortest path distance along the road. However, a heuristic would just be a straight line distance. So ignore the roads. Imagine you could just suddenly, cut through all those buildings and just go in a straight line. Okay, you're not going to actually do that in reality, but you know that that straight line distance is guaranteed to be an underestimate. So that's why this is a really nice heuristic function for this case. And so, so if we have things like where the nodes are location and the cost is time, we can use the distance to the goal divided by the maximum speed. And if the goal is to say collect all coins, and not run out of fuel, the cost is an estimate of how many steps it will take to collect the rest of the coins, refuel, and then return to the goal position. But all of these examples, what we're doing is the heuristic function can be found by solving a simpler or less constrained version of the problem. So another example, kind of outside of Euclidean distance, let's say we're trying to solve a Rubik's Cube. And you could imagine that when you're solving the Rubik's Cube, if we allow you to cheat, by moving colors, from one side of the cube to the other without rotations in certain cases, that would be another example of a heuristic. The idea with applying this to depth first search is now we're going to select the neighbor that is closest to the goal according to the heuristic function. And so this inherits all the advantages and disadvantages of depth first search, but locally at each step we're going to be heading more toward the goal. So if you remember last time when we discussed depth first search, oftentimes we'd end up at nodes that wouldn't have any possible path to the goal. And so if we can avoid nodes like that, we will do better and we'll find the goal sooner. So we're going to select a path whose end is closest to the goal function according to the heuristic. And best first search selects the path on the frontier with the minimal heuristic value. So we're still treating the frontier as a priority queue, but now we're ordered based on the heuristic function. Okay, so what we have here is this is a map with roads represented as a graph. And what you got is you have a straight line distance. So here is A and G is the goal. That straight line distance is 7. Okay? And then likewise, you see E, the distance to the goal, is only 3. Notice that for node E, it's actually much longer than 3. This is okay because that is an underestimate. So if we walk through an example here and we start at A, let's say A is the initial node, and we're doing depth first search, but now selecting things by the heuristic function. So we have 3 nodes to pick from, B, D, and C. So we first pick node B. Now, next we have, if we're doing depth first search informed by a heuristic, we would only consider the neighbors of B. If we're doing a true best first search, we would consider all the nodes in the frontier. So, but regardless of the case, is the best node to pick is going to be E in either case, because E is of distance 3. So then what do we have to select from? Well, again, in either case, we have node F, which is distance 5 to the goal. And then we would select node D, followed by H, followed by G. And we've reached the goal. So this is the path that we have taken. Okay? So clearly, this is not ideal. We have a little bit of an issue here in that we did get to the goal, which is a good thing here, but the route we took was probably longer than it needed to be. If we had picked D in that first iteration, we would have had a much shorter path. However, the reason we didn't pick D and it never came up was because it was never the lowest cost node while we still had B and the neighbors of B directly available. So that's it for now. Stay tuned and we'll talk about how to get around this problem.